Hello, everyone. Well, as Dr. Vito said, I'm going to show you a little bit of what I'm doing for my master's research. I'm working with her and Dr. Marford. So let's start. Oh, there you go. So we know that today is very common to work with merge cubes, seismic merge cubes. So the motivation of this project is um, try to overcome some problems that a merged dataset has. The merged dataset that I am working on is a result of merged two seismic surveys that were acquired at different times with different parameters, geometries, and we found a sharp contrast in amplitudes and in frequencies. There's a mismatch when we look at the sum of these two surveys. So I am exploring the use of the spectral balance and structure-oriented filter to try to overcome these problems that I encountered. Well, my seismic dataset is located in the Gulf of Mexico, in the Matagorda Island. It is an extensive, very extensive seismic dataset. It is 2,800 square kilometers, but for the purpose of this research, I cropped the area only to where the problem is more evident. Here we can see that this is the volume I am using. This yellow line represents the merge between the two surveys, and is where we identify this sharp contrast between the two legacy surveys. As we can see here in the entire data set, we have here the two original surveys that were merged into one. So we don't have the processing reports of these surveys, but we do have some information about them. For example, the bin size, which we can see is slightly different, very small difference, but there is a difference in the number of channels, in the fold, and so on. And here is a representative cross line of the mega merge in which we can see a difference at both sides of the scene. We can see that we have brighter amplitudes at the left area of the line, and we are gonna focus on that difference. So what I did is basically interpretation on the horizons and identifying these discrepancy in the values of amplitudes and frequencies. I basically was doing the quality assessment of the cube, and as I mentioned, I identified this problem, and then by applying two different methods, I will try to see if I can solve that problem in the difference of amplitudes and improve the quality of this data set. Well, as I mentioned, I'm going to use the spectral balance, which is a method that aims to relocate the frequency values. It's different from a bandwidth extension because I am not adding additional frequencies to the existing data set. I'm just relocating the values of the frequencies to its ideal level. And then structure-oriented filter, which is well known to enhance edges. So using the combination of those, I will try to improve the data sets. So here we can see the frequencies before and after spectral balance. In orange, we have the frequency of the original data set. As you can see, it's very poor in content. Everything is located between 15, 10, and 40. And then we have a strong decayment. And with the spectral balance, what we did is extend the range of usable frequencies. And now we have a more flatter spectrum. And we enhanced the usable frequencies of these data sets. It's not included here, but well, after applying SOF, the frequencies are not changing, which is expected because SOF doesn't play with the frequencies of the seismic. Well, here we can see what are the effects of spectral balancing. We have the reduction in the values of the amplitudes, and yeah, we can see that we don't have any dominant frequency after spectral balancing. So let's see how it looks in the seismic data. So let's go to see the results. Here, I'm gonna show you in the following slides. The A is gonna be the original data set. B is gonna be only spectral balance data set. C is gonna be only structure-oriented filtered data set. And D is the combination of both. First spectral balance and then structure-oriented filter. So here we can see there's there you go. The interpreted sections, and we can easily identify where is the seam between the two surveys and all the faults. And yeah, in the spectral balanced seismic lines, we can see that we have more frequency content. We can see that the reflectors become more thin, and we have a little more resolution. So how it impacts in attributes. Now I'm going to show you the attributes that I generated using AASPI. I'm going to go very quickly with this. It's just to show the effects of these two methods. Again, A is the original, B is spectral balance, C is structure-oriented filter, and D is a combination of both. We can see in the original data set how the amplitudes, there is a sharp contrast at both sides of the seam, which is not, it doesn't have any geological sense. If we are interpreting this, we notice that this something weird happening there. And well, after the application of the two methods, we can see that there is a slight improvement. We don't solve the problem of the sharp contrast, but yeah, the amplitudes are more homogenized across the seam. With frequency, we have the same problem. We can see here that there is a contrast. After spectral balance looks much more better, which is something very good, something that we wanted to do, so it's good. With Sobel filter, this is similarity attribute. So we see that we don't have any contrast. So this attribute is not sensitive to the contrast, but it is really sensitive to the two methods applied. So we can see when we apply only spectral balance, some noise showing up. This cube is contaminated with a lot of footprint noise, and that footprint noise is enhanced after spectral balancing. Something that is improved with SOF. We can see that the image is much more clear. And then in the combination of both, we have a combination of both. So something that is really cool is that with spectral balance, we are seeing some small features parallel to the fault that are small faults and discontinuities that spectral balance is helping us to see. This is another geometric attribute that it appears to be not sensitive to any of the methods. There's not a clear difference in the images, like doesn't move anything. So going. And then with spectral attributes, I tried first peak magnitude, and again, the contrast is very evident. And after the use of the combination of the two methods, we still have the contrast, we still see it. And with mean frequency, we have very good results. I mean, we don't have this sharp difference that we are observing here in this figure. Looks like much more homogenized. We don't have contrast like super sharp. So this is a very good result. So after seeing all the results, let's see if these two methods are helping me to improve my geological interpretation or helping me to reveal something that I wasn't able to see in the original data set. So here I am co-rendering 3 attributes: peak frequency, peak magnitude, and Sobel filter. So we can see here in this time slice that there is a contrast again here happening, that after spectral balancing is looking much more better. We have a more homogenized distribution of frequencies, which is good. Sobel filter, so structure-oriented filtering is not helping with that, but is helping in solving some features here, which is good, some stratigraphic edges. But then at the combination of both, we lost a lot of detail. That is something that Dr. Marford mentioned earlier today. So spectral balance, which is supposed to help me to reveal features, small features, is doing something weird in this data set. So to evaluate better if it's helping or not, I took some few examples of the data and how it looks the original, the structure-oriented filter, the spectral balance, and the combination of both. And we can see here that spectral balance is helping me to see these very subtle features that can be interpreted as discontinuities, faults. We have to explore more that are not visible in the original data set. I put here a little crop of this area, and these small features here are showing up after spectral balance. So in this sense, spectral balance is helping me. But then what happens with the stratigraphic edges? Again, coming back to the figure that I showed before, this edge here that seems to be a channel edge, and it can be see here in the seismic sections, is not improved. The visualization is not getting better, it's getting worse. The data is hurt. So are we in presence of a pitfall of a spectral balance? I guess yes. So I'm not gonna read all this, but yeah, some of the conclusions is that yeah, all the attributes that we tested are sensitive to the seam, to the difference in amplitudes, and all of them except of total energy show to be sensitive to the application of a spectral balance and SOF. And well, the footprint that is in high frequencies can create more noise if we don't clean it before applying spectral balancing. And yeah, probably we are in presence of a pitfall of spectral balance, and we have to be careful with the data that we are using as input, and we have to be careful with the frequencies and study better the frequencies of our data to see what are the results of applying these methods. So these are some references. Thank you.